Okay, in this video we're going to take a look at the second derivative and we're going to explore what it tells us. But first let's take a look at this function f of x, which is equal to x cubed, and let's focus on the first derivative. Now recall the first derivative represents the slopes of our tangent lines. So if we were to just sketch in here some tangent line slopes, as we go from left to right here, we can draw some conclusions. So over on this side here, we can see that our derivatives are actually decreasing, right? It's getting less and less steep. So maybe your slope is going from 4 to a slope of, maybe 1/2 over here near the origin, okay? So we can say that our first derivative is decreasing, okay? Now, likewise over here in this region, we see that our derivative or our tangent line slopes are increasing. So maybe you're going from a slope of 1/2 to 1, and then maybe over here it's at like 3, right? So here our derivative is increasing, okay? So again, those tangents are getting steeper. Now, in this region here at the bottom, where our first derivative is decreasing, we say that f is concave down. Do you see how it's bent downward? That is going to happen anytime your first derivative is decreasing. Okay, and so with that we can say that if f is concave down, we say that the second derivative is less than 0. In other words, our second derivative is negative. Now, likewise, in this region up here, if I use green to highlight this region, we can say that in that region, our function f is concave up. Now, this means it's bent upward, okay? And that happens when f prime is increasing, okay? So this is true when the second derivative is greater than 0. So when the second derivative is a positive number, okay? Now right here at the origin, notice that the concavity changes. All right, the concavity changes from negative to positive, okay? If the concavity changes, this is known as an inflection point. That's an important vocab word, an inflection point. And this is a point where the second derivative is equal to 0 and the second derivative changes sign. Okay, so either it goes from positive to negative or negative to positive. So the big takeaway here is if our second derivative is a positive number, our original function f is going to be concave up. And if our second derivative is a negative number, our original function is going to be concave down. We have an inflection point where the concavity changes, all right? And keep in mind, guys, that this original function here, this is a function f of x equals x cubed. So we're using both the first derivative and the second derivative as a tool to tell us about that original function, okay? So again, inflection points, these are special points where the second derivative is equal to 0 and the second derivative changes sign, okay? So it's very similar to our critical points that we saw before where the first derivative was equal to 0 or undefined. And here's a little trick to help you remember this. If the second derivative is positive, your function f is bent upward. And if your second derivative is negative, your function f is bent downward. So we're talking about either positive or negative. That's referring to the second derivative. And if it's a smiley face or a sad face, that's referring to f. Okay, so this little visual here helps you to remember that if we're talking about a positive second derivative, f is bent upward, or what we call concave up. If we have a negative second derivative, then we are talking about a graph of f that is bent downward or concave down. Okay, a couple quick examples where we are looking to algebraically find our concavity intervals and any possible inflection points. So we're going to start with a very simple example, f of x equals x squared. Now we all know what this looks like. Okay, it's a nice parabola, opens upward like this, and you can see that this parabola here, so this is our f, right? This is concave up everywhere. Okay, so our function f is concave up everywhere. So that suggests that the second derivative is positive. Well, let's look at this algebraically. To get to the second derivative, we of course need to first get the first derivative. So our second derivative is just the number 2, right? And so that tells us that our second derivative is greater than 0. Okay, so therefore we see that f is concave up everywhere. And so in this situation, there are no inflection points, right? The concavity never changes, so we don't have any inflection points. Okay, let's take a look at another example. Okay, this time we have a more complicated looking function, but it's still fairly simple. It's a nice polynomial. So let's go through and find our derivative here. And then from there, let's find our second derivative. Okay, just like we did with the first derivative test, we're going to take our second derivative and we're going to set it equal to 0, and we're going to solve. Well, I can take out a GCF of 20x squared. I'm left with x minus 3. And from there, when I set each of these factors equal to 0 and solve, I'm going to get x equals 0 and x equals 3. Now, understand that these are not guaranteed to be inflection points. We have to see a change in sign, a change in concavity on our second derivative. So to see that, what we need to do is make a sign diagram, but this time for the second derivative. So it's the same exact process that we followed for the first derivative. Now, let's work smart here. This 20x squared, that is always going to be positive, right? So we don't have to bother plugging into that. That's always going to be a positive number. So we really just need to focus on this x minus 3 factor. So plug in -1, we're going to get a negative there. Plug in +1, look at that, the signs don't change. We get another negative, and then plug in something like 4, we get a positive. So first understand what these signs mean. All right, these two negatives here suggest that f is concave down. Okay, it's bent downward. This positive suggests that f is concave up. Okay, now 3, when x equals 3, this is our only inflection point. Okay, this 0 is not an inflection point. Okay, yes, it's a point where the second derivative is equal to 0, but the concavity is not changing, so it's not an inflection point. I should also add here that above these values we have 0, because that's where the second derivative was equal to 0. Now, let's further investigate what's happening here by looking at our first derivative. Okay, so if we were to look at our first derivative, let's make a sign diagram for this. Well, before we do that, we have to take our first derivative and set it equal to 0 and solve. So I'm going to take out a 5x cubed. If I do that, I'm left with an x minus a 4. And that is going to produce x equals 0 and x equals 4. So 0 and 4 are points where the first derivative is equal to 0. So if I plug in a -1 into this factor here, it's going to be a negative. And if I plug in a -1 here, it's going to be another negative, so that's going to be a positive. Plug in a +1, well, you're going to have a positive and a negative, so that's a negative. And plug in something like 5, it's going to be a positive. Okay, So if we were to try to put these pieces together and sketch this, this is what we would see. So if we assume that we were able to just use our calculator to get this function for now, later on we'll focus more on how to get this graph using these sign diagrams, okay? But for now, let's just assume that we graphed our original function f of x, and this is what showed up. I marked off some key points here. In no particular order, let's look at this one down here. Notice we have a local min at x equals 4, okay? That's shown right here, and by the way, this would go down forever and up forever, so we would not have an absolute min or max. This point right there is our inflection point, because that is where the concavity is changing. You can see how it's going from being bent downward to bent upward. So the concavity is changing at x equals 3. That's this point up here, right, when x equals 3. And this other point at x equals 0, notice how it showed up on both of these sign diagrams. Okay, so it shows up here on the first derivative sign diagram, all right, and it is a local max because the first derivative is going from positive to negative. Okay, and that's supported by our graph. We can see it's a local max. Now it does show up on the second derivative sign diagram, but again, it's just a random point that we're ignoring on the second derivative because the sign is not changing. So the big conclusion here is that it is not an inflection point. And again, you can see pretty clearly by looking at the graph here in this region, concavity is not changing on each side of x equals 0, right? It's concave down. And finally here, let's just write out our intervals for concavity. So again, we're doing all this to describe f, so we can say that f is concave down all the way from negative infinity to 3. So that's going to include that 0 here. Okay, again, look at the graph. We can see that when x is 0, it's in a region that is concave down. Okay, so f is concave down from negative infinity to positive 3, and it's going to be concave up from positive 3 to infinity, but we're not including that 3 because again, when x is 3, it's an inflection point.